Alrighty, good morning again. Welcome back to College Algebra. Today we're going to expand our discussion of power functions into the discussion of polynomial functions, which is kind of a generalization of power functions. We are also going to be opening up a few new homework, and I'm going to kind of lay out a timeline for test 2 because it's closer than you think. All right, before we get into any of those specifics, I need to get the dot cam going. So let's do that. All righty. I'm good. I think we're good. This, of course, is MAC1105, section 007. It's a lecture, and today is the 22nd. I think, right? Or is it the 23rd? It might even be the 23rd. Oh, it is. It's the 23rd. My bad. All right. Today, we're going to begin talking about polynomial functions. Quadratics that we studied already are an example of polynomial functions, but there are lots of other polynomials also. Linear functions are all polynomial functions. But again, there are many, many more kinds of polynomials besides linear and quadratic. Some of the power functions you've been playing with are polynomial functions, but not all of them. And I'll make clear exactly what is what. The homework associated with this is homework 13. Yeah, 13. No, 12. All right, no. Yep, so this week we're going to be doing homeworks 12 and 13. But homework 13 we probably won't touch today. Probably that will have to wait till Thursday. Any other announcements sort of things? Just say note for exam 2. It's closer than you think. So let's take a look over here real quick. We have just finished homework 11, right? This has come due right now, just became due. If you need an extension on this or any of the old ones, as always, you can email me and request one and I can extend it a little bit for you. Homeworks 12 and 13. 13 is actually in 2 parts. And quiz 4 are what we're going to be working on this week. So we've got really these 3 homeworks in this quiz. And then we will be getting ready for test 2. So next Tuesday, when these things come due, I will be opening up the review for test 2. We'll do another little activity, we'll do another little project, and then we'll be getting ready for test 2. So test 2 is likely going to be a week from this Thursday, guys, just a little over a week away. So please make sure that you've internalized all the feedback that I left for you on test 1. Look at all the comments that I left you on the written work. Look at all the comments that I left in the actual exam itself. Make sure you're learning from those things. Make sure that you're growing beyond where you were a few weeks ago. That's the best way to ensure that things go well in the future. It's just to have that constant, consistent little improvement. But yeah, just wanted to let you know, test 2 is around the corner, much closer than you think. I haven't had a lot of office hour involvement from this class. And I just wanted to remind you how you can come to office hours. If you do have questions you want to ask, any Monday, Wednesday, or Friday, you can click this first link between 1 and 2 p.m. to join a Zoom meeting, and I will help you with whatever problems you want to look at. Or I'll talk about whatever you want to talk about. You know, if you want to go over some old test problems, you want to go over quiz problems, you want to like talk about homework stuff, you want to talk about something else, whatever, you can click this link 1 to 2 p.m. Monday, Wednesday, and Friday, or this link from 11 a.m. to 12 p.m. on Tuesdays and Thursdays to do that. And I want to really encourage you guys to do that if you have anything that you're curious about or want to talk about. So let's be a little bit more quantitative with this. Probably next Thursday. I think that's all the little intro bookkeeping stuff. So let's dive in. So polynomials. I'll give you two definitions. The first one is a polynomial is a sum of power functions where all the powers are greater than or equal to 1. I should say greater than or equal to 0. Constant terms are allowed. Hammy, it's okay. Come over here, lay down, bud. You're all right. So this is kind of one way to think of polynomial functions as coming from the stuff we studied before. So you just take some power functions where all the powers are greater than or equal to 0, i.e. not negative, and add them up, and you will get a polynomial. The more standard definition, but it looks a little scarier, says a polynomial of degree n is an expression of the form an x to the n. And look at that, that's like a power function, right? The n's here are just like keeping track of something. The n here is the power. And this just tells you that that's the coefficient of x to the n plus n minus 1, x to the n minus 1. Here's another power function. It's just one power less. And you continue like this. N minus 2, x to the n minus 2. And you go all the way down till you get to like a2 squared plus a1x plus a0. So in general, this is what polynomials look like. We like to use notation like p of x to describe polynomials to kind of emphasize that they are polynomials. And a few things here. N is a positive integer. And an is not 0. This is the sort of technical definition of a polynomial. And whatever works for you in your mind is fine. They say the same thing. The second one kind of builds in this definition of a degree. So the degree is the largest power of x that shows up anywhere in your polynomial. And it's because we want the polynomial being defined to have degree n that we require that the lead coefficient here is not 0. Because if an were 0, then this would really be a polynomial of degree n minus 1 or something smaller. I know that this second definition looks scary, so let me just show you some examples right away. Examples are the way we learn. P of x equals 6x to the 4 minus 3x cubed plus 5x squared minus 1/3 x plus 7. This is a polynomial. This is a polynomial. The degree here is 4. The lead coefficient is 6. I call it A4 if I really wanted to be picky about it. A4 is 6. So kind of instead of A, B, and C, like we had with quadratics, we have an minus 1, an minus 2. So this would be like A4 because it's attached to x to the 4, A3 because it's attached to x to the 3, A2 because it's attached to x to the 2, A1 because it's attached to x to the 1, and A0. If we want to list the other coefficients, we can. Let's do it. So A3 would be -3. That's the number that is attached to x cubed. A2 would be +5. A1 is -1/3. And A0, the constant term, is 7. So the special name for this guy is the constant term.
I have a question.
Yeah, sure.
So does it matter if, so say if 6x to the 4th was like 6x to the 5th, would it be a to the 5th or would it still be a to the 4th? Because it's like the first one.
So careful a little bit with the language. So we call this A4 rather than A to the 4th. That can confuse people a little bit.
Oh yeah.
Like a power. But we would call that A5. If this was
Okay.
like 6x to the 5, we would call it A5. In general, an is the coefficient of x to the n. So whatever the power is here is the same as the subscript here.
Okay, that makes sense.
We can do an example here where there are a few missing to kind of try to get a feel for that. That can help us with that. Are there any other, before I do that, are there any questions about where these labels or things coming from? Like how we knew the degree was 4, how we knew the lead coefficient was 6, or how we wrote any of these down? Okay, yeah, let's look at another couple of examples then. One of my favorite polynomials, one that you actually saw on a test as a graph, is x cubed minus x. This is a polynomial. The degree here is what? Who can tell me the degree of this polynomial? Oh, sorry, I see it in chat. Yeah, beautiful. Brooke and Andrew both nailed it. Degree here is 3. All right, what's the lead coefficient? I would call it A3, right? Because the leading term here, the highest power term, or the highest degree term, is the cubic term, the x cubed. And yeah, Andrew's correct. It's 1, right? Just like any variable is 1 times that itself, this x cubed is really 1x cubed. Okay, what about the other coefficients? It's a degree 3 polynomial, so it should have A2, should have A1, and should have A0. All of these should exist, but what are they? What is A2? What is the coefficient of the quadratic term here? Very good. Yeah, Kendra nailed it. A2 is 0 because we don't see an x squared here, right? So this is like x cubed plus 0x squared minus x plus 0. So what is A1? Very good, Andrew. Yeah, well, actually, let's be a little bit more careful. So A1 should be the coefficient of x to the 1. Here's the x to the 1 term. Yeah, -1, right? Very good, very good. Okay, and then the other tricky one here, what's the constant term, A0? Yeah, this is 0. In the same way that that the quadratic coefficient, a2 is 0, the coefficient of x squared. Are there any questions about where this information is coming from? This one's a little bit harder to read the other coefficients off from. Okay, just for gits and shiggles, let me see if there's anything sneaky along these lines in your homework. I don't believe there is, but yeah, same sort of shit. Yeah, no, okay, so we need some non-examples. We'll talk about behavior and extrema. But yeah, all right, no. So what about some things that are not polynomials? No, Nala. Oh, damn, this catch is tearing up my catch. All right. This is not a polynomial. It's not a polynomial because it doesn't fit the form of either definition. If you think about the first definition, it says a polynomial is a sum of power functions where all the powers are non-negative integers. This is not a non-negative integer power. Or if you try to fit this into the mold for a degree 3 polynomial, the first power would be 3, then the second power would be 2, then the next power down would have to be 1. But again, this is not a integer power. It's certainly not 1. What is this? F of x here. If I try to write this in that form, this is x cubed minus 2x squared plus 3x to the 1/2 plus 1. So the problem is this guy. Non-integer power of x. So if any of the powers of x are non-integer, automatically that thing is not a polynomial. And here the square root of x is the same as x to the 1/2, which is not an integer. And it's all right. Any questions about why this isn't a polynomial, how this breaks the definition or fails to satisfy the definition? Is this a polynomial? Yeah, good, it's not. Which pieces give us problems here? Good. Yeah, very good. The 1 over x is an x to the -1. What about, so there's another piece here that could be giving us trouble, right? So the 2x is fine. The +1 is fine. -1 over x, that's minus x to the -1. That's a problem. And then plus the square root of 3 times x to the 4th. So we've identified this term as being a problem, right? Here the power is negative. That's no good. Is this term a problem? Yeah, this term's actually okay. Even though the 3 is under a radical, the x is not, right? The power of x here is a non-negative integer. This is okay. And the coefficients can be whatever sort of numbers you want. Doesn't matter. All that matters is that the power of x's are all whole numbers greater than or equal to 0. So this piece isn't a problem, right? This whole piece right here is just fine. The only thing that makes this non-polynomial is this piece. In other words, square root of 3 times x to the 4 is polynomial. He doesn't have any problems. All right. Let's see. Is there anything else we should talk about here? I think we're pretty good on this. So the next few things that we do need to discuss are extrema, right? Mins and maxes. We got to get the language down for those. And I really want to talk about factoring. Factoring is super duper important, but I think the order your homework introduces these, they talk about extrema and symmetries. So yeah, we gotta do that first. All right. Any questions on any of these examples? What makes something a polynomial or what makes something not?
I have one more question.
Yeah, sure, Brooke.
Does it matter the order that they're in? So if since x to the 4th is at the end, does it matter? Would that be the degree or would 1 be the degree?
It's a good question. Yeah, so let's do one more where things are not so clear from the start. The order does not matter. So a quick answer here. So if I had something like 1 minus 7x squared plus 3x minus x to the 14. This is a polynomial. Here the degree would be 14. And the lead coefficient would be -1. Because that's the coefficient of the dominant term. So the order you write these things in doesn't matter. The sort of standard way of writing these things is with the largest power first and then going down. But you'll see them written out of order often. And when they're written out of order, that doesn't change the degree or the lead coefficient. So the degree is always the largest power of x that shows up. And the lead coefficient is always whatever number is attached to that largest power. Are there any other questions on these sort of definitions, examples, non-examples? Alrighty then. So let's talk about mins and maxes. we use the term relative and global. Local. Oh no, they use the terms local and absolute, but later they use, yeah, relative. Whatever, we introduce all of them. So mins and maxes. These can be discussed for any function, but kind of the natural place to start talking about them is when we're talking about polynomials, because polynomials are the simplest functions that have lots of these things. So first, I need to give you some definitions. A function f of x has an absolute, another word for this is global maximum at x equals c if f of c is greater than or equal to f of x for all x in the domain of f. So if the y value, f of c, is bigger than all the other y values, f of x, then at x equals c, we say we have an absolute or global maximum. Absolute and global are interchangeable terms. Your homework contains both. But these absolute and global mean the same thing. Okay, I've got 3 more definitions that look a lot like this. A function f of x has a local, and then the kind of corresponding similar term here is relative max at x equals c if f of c is bigger than f of x for all x near c. So you can kind of compare the ideas. And the kind of absolute or global corresponds to the idea that this is, comparing the y value there to all the y values. Local or relative says you're comparing the y value there to all the ones nearby, right? So local or relative kind of means compared to the stuff nearby, this is the biggest. And absolute and global says compared to everything, this is the biggest. And then if you want to interchange the word maximum for the word minimum, you just have to swap the inequalities around. I'll go ahead and write them down. This is a lot of words. A function f of x has an absolute, aka global minimum at x equals c if f of c is smaller than f of x for all x in the domain of f, and the function f of x has a local, aka relative, at x equals c, if f of c is less than or equal to f of x for all x near c. All right, so these are all the definitions for mins and maxes. It's a bunch of word soup. So there are some pictures that go along with this that I think will be very helpful here. Do something like this to start. Okay, so here's a graph. We'll say this is the function f of x. And I'm just going to pick some numbers here. So I'm going to call this 2. 3. 4. 5. And we're going to say this is the whole graph, right? This is the whole function. Okay. So what's going on here? Let me, I know that things aren't perfectly to scale here, but let me also call this 1. I'll call this 7. All right. So the thing that's happening at 2 here, if you look, this is actually the lowest point on the graph anywhere, right? The graph never dips below this. So we would say f of x has an absolute min at x equals 2. It's also a local min. How do I want to say this? Because it's the lowest point on the graph anywhere, it's an absolute min. And if I pay attention just to what's going on nearby, that's the lowest point as well. So this is a local min, and it's also an absolute min. What's going on at 3 here? What feature does this function exhibit at x equals 3? Well, is this point the tallest point anywhere on the graph?
No.
So it's not an absolute max. But if I look just in this little window, is that the tallest point in this little window?
Yes.
Yeah, it is, right? So if I am only considering x's that are close to 3, is this the tallest point there? Yeah, it is. So f of x has a local max at x equals 3. Okay, moving along. What's going on at 4 here? This certainly isn't the lowest point anywhere on the graph, but if I draw a little window around x equals 4, that is the lowest point in that window. So what kind of feature does this function exhibit at x equals 4?
It has a local minimum.
Very good. All right, what's going on at 5? Going on over here? Very good, a global or absolute max. And also, if I was looking only within this little window, that is the tallest point there as well, right? So this is also, I should use a semicolons or independent clauses. This is also a local max. Cool stuff, right? So these are local and global, or absolute and local extrema. This is the absolute min. It's also a local min. This is just a local max. This is just a local min. This is the absolute max, and it also happens to be a local max. Is there anything interesting going on at 7 or at 1? Let's look at 1 over here. If I draw a little window around this guy, that's the tallest point in that window, isn't it? So at x equals 1, we have again a local max. And at x equals 7, we have a local min. This is the smallest point in this window. If I draw a little window around it, that's the lowest point in there. So this is a local min. Even though it doesn't have the same sort of shape as the others. I'm sorry, my dog keeps crying. I gotta see what he means. I think he's outside. Hammy, come here, bub. Come on, big boy. You want that? Yeah, come on. Good boy. Okay. Do we feel comfortable recognizing these things? Are there any questions about why any of these features that we've listed here are what they are? I think the way a lot of people remember this is the bottom of a valley is always a local min, and the top of a hill is always a local max. And then the highest point on the graph anywhere is the global or absolute max, and the lowest point on the graph anywhere is a global or absolute min. But you do have to be on the lookout for weird things like this. Right? So making sure that you know and are comfortable with these definitions is important. The other thing we need to talk about is the sort of language that we use to describe where the min or max is compared to what the min or max is. So let me draw for you another example here. Let's do it by not quite to scale, but that's okay. Okay. So here's a graph, and then I'll call this y equals p of x. Why not? Just to get used to this new notation. I want to describe any mins or maxes for the function p of x graphed above. And now instead of having like a finite domain where things chop off, we've got these arrows. That does make life a little bit different. So who can help me? What sort of extrema, that's the, by the way, the name for all of these things put together, mins and maxes. Together, these are called extrema. So what's going on here? Yeah.
-1, it'd be a local max, right?
Good. There is a, so be careful with the language. I would say p of x has a local max. You're absolutely correct. Local max at x equals -1. I'm going to give myself a little bit of space here because I want to talk about something else. What else is going on? What other extrema does this function have? So this, if I draw a little window around this, is that the tallest point in that window? Yes. So this is a local max. There is a local max at -1. What about this? What is this? Yeah, good. There's a local min at x equals +1. So we'd say p of x has a local min at x equals +1. Okay. No global max, right? Because this arrow goes up forever and ever and ever, amen. So there is no tallest point on the graph, right? This function continues going up like this, and it'll get as tall as you want. So there is no tallest point on the graph. Similarly, this arrow goes down forever and ever and ever, amen. So there is no lowest point on the graph. So we'd say P of x has no absolute max or min. But the thing I want to talk about here, when I say there is a local max at -1, and this language is important, I'm telling you where. Where is the max? The max is at -1. But I'm not telling you what is the max. So we should add on here, and the max value is whatever this y value is right here, which is 1. And similarly here, when I'm describing this min, it would be nice to tell the reader what the min value is. So I'll say, and the min value is -1. If we wanted to be really careful, we would say the min value, max value there, in case there were other maxes or mins. So when we ask where is the max, that's always the x value. When we ask what is the max, that's always the y value. Similarly, when we ask where is the min, that's always the x value. And if I ask what is the min, that's always the y value. So kind of the point I wanted to make with this guy is and this is an important distinction. Just like when I ask where is a function increasing, I'm asking for what x values is the function increasing. Remember when we talked about that? Always open intervals of x values. When I ask where is something happening, I'm always asking for the x values or the input at which that feature occurs. And in the context of mins and maxes, if I ask you what is the min or max value, what is it? That's the y value or the output. Yeah, Mark asked a cool question in chat. So how many global maxes can I have? How many global mins can I have? How many local maxes can I have? How many local mins can I have? And precisely what you said, Mark, is correct. Yeah, you can have only one global max at most, and only one global min at most. So you could have that same min or max. This is precisely the language we're talking about down here. So in the example you have there where f of 5 is 20 and f of 8 is 20, and the graph never goes above 20, you have one max value, 20. But that max value occurs multiple times at 5 and at 8. Does that make sense? Yeah, it's a neat question. Let me try to illustrate what Mark was asking there, because I think that's a really good question. But first, I want to make sure we're comfy with what we've said here. Are there any questions on this example? Okay. So yeah. One of my favorite examples I'm not going to use precisely the example you talk about that much, but something a little bit similar. Let's call this 4. Let's call this negative. Oh, so there absolutely are functions that do this. Just to make things simple, I'll call this 1, 2, 3, 4, -1, -2, -3, and -4. Not only are there functions that look just like this, there are functions that look just like this and go on and on and on like this forever. So just for fun, let me call this function s of x. And we'll say that the domain stops here, right? That it doesn't go on beyond these points. So one way I could phrase what's going on here, I could say that the absolute max for the function s of x is 4, and it occurs at -3 and +1. So there's only one max value. There's only one largest y value, but it shows up multiple times. So the kind of language you use is important here. The absolute max for the function is 4, right? We're asking what is the max? 4 is the max. Where is the max? Well, that max occurs more than once. That max shows up at -3, and it shows up again at +1. If this pattern were to continue, it would show up again at +5. The absolute min for this function is -4, right? It's the smallest y value that shows up anywhere on the graph. And it occurs twice also. It occurs at x equals -1 and x equals 3. Now these, in addition to being absolute extrema, are local extrema. So we could also say local maxes at x equals 3 and 1, sorry, -3 and x equals 1, whose max values are 4, and there are local mins at x equals -1 and x equals 3, whose min values are -4. In other words, these guys are local and absolute maxes. It's the same max value. I can't have more than one max value. In other words, I can't have more than one y value being the biggest, but I can have one biggest y value show up multiple times on the graph. So here, these are both points where our max value is attained. And they happen to both be local and absolute maxes. These are local and absolute minima. You guys feel comfy with that? So an inflection point, do they talk about inflection points in this? I don't see anything in the homework. I don't think we asked you guys, the textbook mentions inflection points, but I don't think we hold you responsible for that in this section. So an inflection point is a place where curvature changes, and that's not something that is really appropriate to discuss in college algebra. Technically, this is an inflection point. This is an inflection point. This is an inflection point. But we'll talk about that after you guys have a little bit of calculus under your belt. We'll come back and talk about inflection points in Calc 2, or sorry, Calc 1. Yeah, don't worry about those for now. So we're comfy with local maxes, local mins, absolute mins, finding them on the graph, labeling them, the difference between the x and the y value. Right, the x value is always the location. The y value is the min or max value itself. Okay. I'm doing on time, 10:30. So the other thing I wanted to talk to you guys about today, two other things I want to talk to you about today is end behavior for polynomials, and then factoring and solving polynomial equations. We've talked about those symmetries in the past. There's nothing special going on there. But we do need to talk about end behavior. Hey baby, what's up? I'm teaching. It's all right. I'll take care of it later. Don't worry about it. All right, I love you. Bye. Okay. Yeah. So we want to talk about and behavior in factoring. The symmetries here are the same symmetries we discussed when we talked about power functions. And we did talk about those in full generality then, so we don't need to go back to that. But I do want to talk a little bit more about end behaviors for polynomial functions. The good news is that the notation is the same. You guys remember the goes to notation. So if you have something over here that goes like this, and something over here that goes like this, I don't really care what happens in between. For any function like this, I would say as x goes to negative infinity, as we wander far off to the left, the y values are going up. Let's say y goes to positive infinity. And over here, we'd say as x goes to positive infinity, y is going down to negative infinity. The type of functions that exhibit this behavior, let me say this another way. The end behavior is determined entirely by the leading term. So these would be any polynomial with an odd degree, and in this case, a negative lead coefficient. All right. So if you want to know the end behavior of your function, you need to know the degree and the lead coefficient. And then the rules are the same as they were for power functions. It's just that you apply those rules strictly to this first term. So same rules for power functions. All right, I'll go ahead and draw all of them here. It doesn't hurt to do that. But then we'll look at one or two explicit examples. So if I have a it does whatever, but then on this side it goes up. We would say this as x goes to negative infinity, y is going to negative infinity, and as x goes to positive infinity, y is going to positive infinity. Because as I wander far off to the left, as x goes to negative infinity, y is going down. Right, maybe it does all sorts of weird shit, but eventually, as I go off to the left, y's go down. So as x goes to negative infinity, wander off to the left, y goes to negative infinity, y goes down. The opposite thing happens on the right. As x goes to positive infinity, as I wander really far in this direction, the y values eventually go up. This happens for any polynomial of odd degree and positive lead coefficient. So you notice it really is the same rules that we had for power functions, right? For a power function, we just had odd power, negative coefficient, odd power, positive coefficient. So what we're doing is we're saying that the lead term, the highest power term, is the one that determines the end behavior. The other two cases here, we can go up on both sides, doing whatever sort of bizarre, silly stuff in between. This is described by saying as x goes to negative infinity, y goes to positive infinity, and as x goes to positive infinity, y goes to positive infinity. This would be an even degree and a positive lead coefficient. And then finally, you can go down on both sides. And this will happen as x goes to negative infinity, y goes to negative infinity, and as x goes to positive infinity, y goes to negative infinity. This is an even degree and a negative lead coefficient. So it's exactly the same stuff we had for power functions. The idea is you just apply those rules to the lead term, the term of highest degree. So I'll look at one example here with you, and then we're going to talk a little bit about factoring. Factoring is sort of the most important thing in this section. We will pick up on Thursday talking more about factoring, and then we're going to talk about rational functions. So hopefully this is all familiar to you. It's the same things that we saw before. Same pictures, same notation here, more or less the exact same rules, just instead of the word power, you have the word degree, and instead of coefficient, you have lead coefficient. So for example, I could ask you to state the end behavior of the polynomial p of x equals x minus x cubed. And we know the answer here is going to say as x goes to negative infinity, y goes to something, and as x goes to positive infinity, y goes to something. So what's going on here? What's the degree? And what's the lead coefficient? Degree first. What is the degree of this polynomial? Yeah, good. 3, right? The largest power of x anywhere is 3. So the degree here is 3, which is odd. What's the lead coefficient? Good, -1, right? The number multiplying the dominant term there is the lead coefficient. That's -1, which is, of course, negative. So this function has a odd degree and a negative lead coefficient. That means he's going to have end behavior like this, right? Odd degree, negative lead coefficient. It's going to go up on the left and down on the right. So up on the left means as x goes to negative infinity, y is going to go to positive infinity. And down on the right means as x goes to positive infinity, y is going to go to negative infinity. Are we all comfy with how we got these? Nothing too crazy, right? Okay. So the last thing I'd like to do is show you a few factoring tricks. And this is where we will pick it up next time. Factoring polynomials. Some common tricks. Or tools. First, you can factor the GCF. Right? This is something that we do all the time. So if I gave you something like, how about x to the 5 minus 2x to the 4 plus 1x cubed, you could begin here by saying, okay, this has an x cubed, this has an x to the 4, this has an x to the 5. So the greatest common factor between these three terms is x cubed. I can bring out an x cubed. And then what's left? Well, x to the 5, if you divide it by x cubed, it's going to give you x squared. Negative 2x to the 4, if you divide it by x cubed, is going to be just negative 2x. And x cubed, if you divide it by x cubed, is just going to be 1. Don't forget this 1. People often forget this. Right? If you factor something out, if the whole thing comes out, then what you're going to get there is a 1, not a 0 or not nothing. And the swift way to check is to imagine distributing this back over these terms. Make sure you would get the original. So this is factoring out the greatest common factor, right? GCF. The next most important tool or trick is called the difference of squares. And we've referenced this a few times in the past. This just says, if you have something of the form a squared minus b squared, that can always be factored as a minus b times a plus b. So for example, I have something like x squared minus 16. Well, a is like x and b is like 4. 16 is like 4 squared. So I could factor this as x minus 4 times x plus 4. Or if you had something like 1 minus x to the 6, this is not as obviously a difference of squares, but 6 is x to the 6 is x cubed squared. So this is the same as 1 minus x cubed times 1 plus x cubed. And you can get pretty creative with this difference of square shit. So this is a very useful trick. There is a thing called a difference and sum of cubes. And this says that if you have a cubed minus b cubed, that can be factored as a minus b times a squared plus ab plus b squared. And if this were an a cubed plus b cubed, you could factor this as a plus b times a squared minus ab plus b squared. Some people like to write these together in one thing. As a cubed plus or minus b cubed equals a plus or minus b times a squared minus plus ab plus b squared. The way you remember this is by remembering the shape and using the acronym SOAP. S standing for same, O standing for opposite, AP standing for always positive. So people remember this as SOAP. Same sign, opposite sign, and then these guys mean always positive. I won't require you to know the sum or difference of cubes formula, but it is very useful. So I wanted to show it to you. Right? This is a useful trick that can get you out of a lot of tough situations, but you're not required to know it. The last sort of important factoring trick is the AC method, which we've already gone over, but I will show you another couple examples of starting next time. So on Thursday, we're going to come in, we're going to talk more about factoring polynomials. I will work lots and lots of examples for you guys. We'll solve equations by factoring polynomials. And then we're going to start talking about rational functions. And rational functions have all sorts of interesting shit going on. But in the meantime, please get into this homework, start working on the first few problems. They are not too bad. I think you will find that there are a lot of connections to what we were doing last week with power functions. And it should not give you too much of a headache. If you do have any sort of headaches, though, don't hesitate to come by office hours. I'll be going there now, or right at 11. And I'm happy to sit there and work problems with you, talk about things, whatever you'd like to do. Any burning questions for me before we sign out? Alrighty, just for fun, if you want to, this can be factored further. If you factor this piece now using the AC method, you will get the thing factored all the way down. These can each be factored further using the sum and difference of cubes. So if you want a good exercise to practice your factoring skills, try to break this all the way down by factoring the quadratic here. Try to break these all the way down by using the sum and difference of cubes here. That is it. I will see you guys next time. Please do work on that homework.